Hello and welcome to today's lesson looking at simple harmonic motion. So in today's lesson we're going to try and understand and apply the conditions of simple harmonic motion to moving objects. Now this particular part of the course is found in the AQA A-Level Physics section of Further Mechanics, which is found in paper 1 of A-Level Physics but not found on AS Physics. So what are we going to try and do in today's lesson? Well, we're going to try and describe the characteristics of simple harmonic motion, explain the conditions we need for simple harmonic motion, and use the equations which detail simple harmonic motion, which links into the following part of the AQA A-Level Physics specification. And as you can see, in this part of the course, which again resides in the periodic motion, the further mechanics section, which is found in paper 1, you've got to analyse the characteristics of simple harmonic motion, you've got to state the condition of simple harmonic motion, the equations of simple harmonic motion, and then understand how you can derive quantities from graphical representations of simple harmonic motion. Now, objects can carry out what we call oscillating motion based on Newton's laws of motion. But what do we mean by oscillating motion? Well, oscillating motion is when objects move either side of an equilibrium position in the same plane. But what do we mean by equilibrium position? Well, the equilibrium position can be considered the midpoint of the motion. It can be the position in the motion where the object resides under no force. It can be the position in the motion where the object is in its lowest potential energy state. You could consider it the position in the motion where the object wishes to reside. And you understand the fact that an oscillating object always wishes to return to equilibrium. However, it can't return to equilibrium because it's undergoing motion, so it'll have inertia, which will actually mean that it can never actually rest at equilibrium. Now, basically, oscillations or oscillating motion is the motion back and forth about a fixed point in a straight line in the same plane. It's the repetitive motion along one plane of motion about an equilibrium position. So what can we have as examples of oscillating motion in the real world? Well, you can have a swing, because in a swing the object's going backwards and forwards, backwards and forwards, backwards and forwards in one plane of motion. The same can be true for a rocking horse. The rocking horse is going backwards and forwards, backwards and forwards, backwards and forwards in one plane of motion. The same for a grandfather clock. The pendulum in the grandfather clock is moving backwards and forwards in one plane of motion. The pendula in this Newton's cradle are moving backwards and forwards in one plane of motion. Now, we've used the word pendulum a number of times. Well, a pendulum is just a broad name given to any mass swinging with an oscillating motion. Now, the most famous example might actually be the chandeliers moving backwards and forwards in Pisa Cathedral, because they were observed by Galileo in the 17th century, and he was able to deduce from that some truths about objects undergoing oscillating motion. But there's actually a special case in oscillating motion, and we call that particular special case simple harmonic motion. Now, what's the difference between oscillating motion and simple harmonic motion, and what's so special about simple harmonic motion? Well, simple harmonic motion is a special case of oscillating motion, and it's caused by a force that repeatedly acts to restore a moving object to its equilibrium position. Now, because it's trying to restore the oscillator to the equilibrium position, we in physics call it the restoring force. So the restoring force is always acting in the opposite direction to motion, as you want to move the object back to equilibrium, back to the center of the oscillation. So the force is always acting as a negative. And the further away you are from equilibrium, the larger the force required to put it back to equilibrium. So you can say the restoring force is directly proportional to the displacement from equilibrium. And at equilibrium, because it's at the position it wants to be in, there's no restoring force. Now, because the restoring force is a resultant force, and the resultant force always causes an acceleration, the acceleration on an object is directly proportional to the restoring force, which is directly proportional to the displacement from equilibrium. Because the greater the displacement from equilibrium, the greater the restoring force, the greater the acceleration experienced by the object. And when you're at equilibrium position, the harmonic oscillator will experience no acceleration, so will have no restoring force acting upon it. Now, we can define simple harmonic motion in terms of acceleration and displacement. Now, what we've got to remember is that this can be represented with the following equation. Acceleration is directly proportional to displacement, but not only that, it's the negative displacement because it's always acting in the opposite direction to the displacement because it always wants to oppose the displacement to get back to the center. Now, you've got to consider both those ideas, the proportionality and the negative part, to get a thorough understanding of simple harmonic motion. But this is a fundamental truth. If you ever see an equation, and in that equation, acceleration is directly proportional to negative displacement, well, the object which is being described by the equation must be undergoing simple harmonic motion. So if you were ever asked to prove if an object is undergoing simple harmonic motion, you must get an equation detailing its motion, and in that equation, acceleration must be directly proportional to negative displacement. Now, we can also consider these particular conditions from another viewpoint, from another thought process, because if we consider an object undergoing circular motion, in which direction does the resultant force act in? Well, in the circular motion, there's a centripetal force. The centripetal force literally means the center-seeking force. It's always acting towards the center of the rotation. Now, which direction will the centripetal acceleration act in? Well, because the acceleration always acts in the same direction as the resultant force, it's the Newton's laws of motion, it must be in the same direction as the centripetal force towards the center of the circle. Now, if we consider that the force and the acceleration are trying to make the object move to the equilibrium position, the center of the circle. But why doesn't it? Well, it's got inertia because it's undergoing motion, so it gives this circular path. But let's now consider simple harmonic motion. Now, that's not when an object's going in a circle, rather when the object is oscillating backwards and forwards in the same plane. Now, we can represent back and forth motion with a positive and a negative, with a positive being in one direction, negative being in the other direction. Now, you can decide which direction is positive and you can decide which direction is negative. Now, let's define the equilibrium position as the position where the pendulum would hang if no force was placed upon it, where it would rest naturally, so that would be in the center of the oscillation. Now, you can find the equilibrium position of any oscillator in the real world by just letting it hang freely. Now, what do we know? In simple harmonic motion, the resultant force always acts towards the center of the oscillation, the equilibrium position, which is actually very similar to circular motion, where the resultant force always acts to the center of rotation. Now, the restoring acceleration will act in the same direction as the restoring force towards the center of the oscillation. Now, the restoring force of simple harmonic motion is equivalent to the centripetal force of circular motion, because both forces are trying to make the object reside in its lowest energy state. Now, the centripetal force wants to put the object to the center of the rotation. The restoring force wants to put the object towards the center of the oscillation, but both forces will never actually get the object to do so because the object is already in motion, so the object will have inertia, so the combination of inertia and the force produces the motion which you observe, either simple harmonic motion or circular motion. So this actually shows us that simple harmonic motion and circular motion obey the same laws of physics. The only difference is each motion has a different reference point for its center. So it shows that simple harmonic motion and circular motion are both derived from Newton's laws of motion. They're the same physics principle, but from different frames of reference. So what can we say? We can say that the restoring force always acts in the opposite direction to displacement, but is proportional to displacement, and it wants to bring the oscillator back to the equilibrium point, which is where the object would be at rest in its lowest position. So let's represent this mathematically. We know that the restoring force is directly proportional to negative displacement. Or we can say acceleration is directly proportional to negative displacement. Why is that? Because we know that F equals ma, so force and acceleration themselves are directly proportional. So what does the negative sign mean? It means to suggest that the force and the acceleration are acting in the opposite direction to displacement. So if the object is displaced to the left, the acceleration acts to the right. If the object is displaced upwards, the force of the acceleration will act downwards. It's always opposing the displacement to move the object back to the center of its oscillation. So the same principle shown before, because we know that the resultant force and acceleration always act in the same direction. So either the equation can be stated as the condition required for an oscillator to be acting as a simple harmonic oscillator. So let's now try to put this into words. So for an object to be moving with simple harmonic motion, its acceleration must satisfy two conditions. Condition 1, the acceleration is proportional to the displacement. And secondly, the acceleration is in the opposite direction to displacement. It's towards the equilibrium position. Now we consider the acceleration in simple harmonic motion to be a restoring acceleration, as it always wishes to bring the object back to equilibrium. So these are the two conditions needed for simple harmonic motion to occur. And it's a very, very, very common examination question for you to be asked, what are the two conditions of simple harmonic motion? So now we've got the actual conditions laid out, let's consider the equations of simple harmonic motion by looking at the motion of a pendulum. So again, what's a pendulum? It's a name given to any mass carrying out oscillating motion. So if the pendulum is carrying out simple harmonic motion, it must have a restoring force directly proportional to the displacement from the equilibrium position in the opposite direction. So we're now going to consider the equations of simple harmonic motion by looking at the motion of a pendulum undergoing one cycle. Okay, now again, we're going to define positive and negative in particular directions, but it's just arbitrary. We can swap the positives and negatives around if we wanted to. So one cycle of a simple harmonic oscillator is equivalent to one cycle of a wave, or one rotation of circular motion. So therefore the phase difference of one cycle in simple harmonic motion is equal to 2 pi radians, or 360 degrees. Now note, these different oscillators can have different phase differences because they might not always be the same difference in their cycle apart from each other. Now oscillators can have a phase difference, and that's basically how much an oscillator will lag behind another oscillator. So let's consider what's going on. So we're going to define one cycle is when the pendulum bob is displaced in the negative direction of point 1. It's then released and swings through equilibrium position of point 2. Then it's going to reach point 3 on the opposite side of its motion. It's then going to swing back to go through the equilibrium position again of point 4. And it's going to go back to where it starts to complete its full cycle at point 5. So at point 1, what we can say here is the pendulum has maximum displacement in the negative direction. Now we're just going to define going to the left in this example is negative. It doesn't have to be negative if you don't want it to be, but we're going to assume it is in this particular example. Then at point 2, it's got zero displacement from equilibrium. At point 3, it's got maximum positive displacement from equilibrium. Point 4, it's got zero displacement from equilibrium. In point 5, completed the cycle, it's now got maximum negative displacement again. So let's now consider A, the amplitude is the maximum possible displacement from equilibrium. So at point 1, what do we know? That the displacement was negative A. Here at point 2, at equilibrium, the displacement is 0. At point 3, the displacement is A. Okay, because it's the maximum displacement. Here is 0, and once again it goes back to negative x or negative a. Now why is it not stayed at equilibrium? Well, it's got inertia, so it will go past the equilibrium position. So if we consider the displacement of a pendulum, we'll get the following graph. So we've got maximum amplitude, we've then got 0 displacement, maximum negative displacement, which is the negative amplitude, back to 0 again, so forth, so forth, so forth. So it can be shown as the following. It links in like this. So it looks very, very similar to actually the cosine function graph which you can find. So if you look at your displacement time graph, it actually plots out a cosine curve. It starts off at positive displacement, which is the maximum positive displacement of the amplitude. You then go to 0. You then go to the maximum negative displacement, which is the negative amplitude. You then go back to equilibrium, so the displacement is 0, and it goes through like that. So you've got to actually understand that the equation for displacement includes a cosine term. Now here's the equation. the displacement for a bob from equilibrium is equal to A, the amplitude, times by cos 2 pi ft, where f is the frequency of the oscillation and t is the part of the cycle in which you want to know the displacement from. So if it asked you what is the displacement equilibrium at 2.3 seconds, well, you would t equals 2.3. Now, obviously, please be mindful of the fact that we're going to be working in radians. So now we know that frequency is equal to 1 over time period. Well, we can sub in. Well, f equals 1 over t, where big T is the time period and small t is just the time given in the question, the time you want to work out the displacement for. So we now know that x is equal to A cos 2 pi small t over big T. Now, because this means as it's displaced more, that's going to actually go closer and closer and closer to 1. Okay, so as a result, we can only use this approximation, okay, with small angles. It's actually only technically true when the displacement of the oscillator is less than 10 degrees, but this is an equation you've got to memorize, that you don't need to memorize because it's given in your equation book, but you do need to understand what the terms are, and you do need to understand what it shows, and you do need to understand your assumptions. So we can show the link like this, which actually shows the idea that circular motion and simple harmonic motion are exactly the same principle, just in different frames of reference. So they actually are the same particular laws of physics. Now we can calculate the phase difference between two oscillators in simple harmonic motion, which is just the angular difference for the displacement between two successive oscillations, i.e. the difference between where they are in their oscillations, in the cycles of their oscillation. Now it only works when the oscillators have the same frequency or wavelength, that they are coherent with each other. So we know the phase difference is 2 pi small t over big T, where small t is the time in the actual journey in the oscillation, and big T is the time for one complete oscillation. So it's the difference in swing cycle between the two pendulums, which is shown in this following animation. Now, let's now consider the velocity. So, if we now have a displacement of x, well, once you've got a maximum displacement, you're going to have a zero velocity. At that instant of maximum displacement, at that instance of when you've got the amplitude as your displacement, your velocity will be zero, because you can't go any further than the maximum point possible. So it has stopped moving at the maximum displacement. But when it gets to equilibrium, the velocity will be a maximum. Now, why is that? Because there's no longer a restoring force on the object, because it's at the equilibrium position. So there's no more restoring force trying to put it towards equilibrium, because it's there. So if F equals ma, if there's no restoring force, there's no acceleration. So it's had its highest speed possible, but its constant speed, which is its maximum velocity. Now again, it'll continue to move through equilibrium because we've got inertia, so it'll continue to move through. So it's still carrying the laws of motion. So it now gets to this part of the journey, and its velocity once again has become zero. It then goes back to here, it has a maximum velocity, and then it goes through because it has inertia, and it goes back to here, and then we'll have a zero velocity again. So what do we know? When you've got a maximum displacement, you've got a minimum velocity. When you've got a minimum displacement, you've got a maximum velocity. Now, this is our equation to work out the velocity of a pendulum or any simple harmonic oscillator. Now, we've got a plus or minus in the equation because we can get a positive or negative velocity in the direction it's moving, because it's going backwards and forwards, backwards and forwards, backwards and forwards, backwards and forwards. You're going to get a positive velocity and a negative velocity from its direction. So what do we know the equation is? Well, it's equal to plus or minus 2 pi f, or angular velocity, omega, times by the square root of the amplitude squared minus the displacement at that point in the cycle squared. Now, this is actually extremely interesting, because the maximum velocity occurs in the middle of the swing, which is when the displacement from equilibrium is zero, so x equals 0. So let's pop that into our equation. So we now know that x equals 0, so it's going to be plus or minus 2 pi f times by the square root of a squared minus 0 squared, which is just going to be a squared. So the square root of a squared is a. So now the maximum possible velocity for an object is plus or minus 2 pi f times by a, the amplitude. Now why have we got a plus or minus? Because it depends on the direction the oscillator is moving in, and this will be the velocity when the object, the oscillator, is at equilibrium, because that's when you have the maximum possible velocity. Now again, these equations are given to you in your equation book, so you don't need to memorize them, but you need to know what the terms mean and what it's actually representing. What we mean by maximum velocity, what we just mean by velocity. And then finally, let's consider acceleration. Now let's just remember one key thing. Resultant force and acceleration are proportional to the displacement. Okay, so, but the force and the acceleration act in the opposite direction to the displacement. So here, because the displacement is a maximum, the acceleration is a maximum, but it's acting in the opposite direction to displacement. So whilst the displacement's acting to the left, the acceleration's acting to the right. When it gets here, there's no displacement from equilibrium, there's no restoring force, there's no acceleration. When it gets to here, we've got a maximum displacement, so a maximum restoring force, so a maximum acceleration. But the acceleration acts to the left, because the displacement's acting to the right. We get back to here again, no displacement, no force, no acceleration, and then back to where we start again. We return to maximum acceleration and maximum displacement, but they're in opposite directions to each other. So what do we know now? When we've got maximum displacement, we have minimum velocity but maximum acceleration, and then when we have a minimum displacement, we have a maximum velocity but a minimum acceleration. So the displacement and acceleration are always proportional to each other but in opposite directions, and the velocity of the oscillator is always opposite compared to the displacement and acceleration of the oscillator. So the acceleration of the bob of an oscillator at displacement x is given by the equation a is equals to minus 2 pi f, or omega squared x, which makes sense because we originally said that for simple harmonic motion we need the relationship acceleration is directly proportional to negative displacement, so the acceleration acts in the opposite direction to displacement. Now, maximum acceleration occurs at the ends of the swing where the displacement is at a maximum, so it's at its amplitude, so x at that point equals a, so the maximum acceleration, which is experienced at the amplitude, and maximum displacement is equal to minus omega squared, or minus 2 pi f squared, a, where a is amplitude. So this makes sense. So actually our equation is a equals minus omega squared x, which therefore it shows you that a is directly proportional to minus x, because a is just maximum x. So the proportionality constant in this particular example is omega squared. So these equations are given to you in your equation book. You don't need to memorize them, but you need to understand what it shows, what the assumptions are, and what all the terms are. So let's summarize what we've learned in today's lesson. Right, so here are equations for simple harmonic motion. Okay, now again, these equations are given to you in your equation book, but you don't need to memorize them. You need to understand what they show and when you use them. Okay, so you need to understand what you would use them for in a question. So x equals a cos 2 pi ft. So that's used to work out the displacement from equilibrium position at a particular time t in the motion of the simple harmonic oscillator. X equals a, well, that's the maximum possible displacement from equilibrium, so x, the displacement, will equal the amplitude a. Okay, this equation b equals plus or minus 2 pi f, or omega, times by a squared, the square root of a squared minus x squared, is used to work out the velocity of the particular time t in the motion, whilst x equals plus or minus 2 pi f, or omega, times by a is used to work out the velocity at equilibrium position in the motion at maximum. Whilst here in the restoring acceleration, this is the equation used to work out acceleration any point in the motion. A equals minus omega squared x, and to work out the maximum acceleration, which occurs at the maximum displacement at the amplitude, we know that A equals minus omega squared A, and remember, this is proof that it's undergoing simple harmonic motion because A is directly proportional to negative x. So, what have we learnt in today's lesson? We can hopefully analyse the characteristics of simple harmonic motion, state the condition for simple harmonic motion, understand the equations of simple harmonic motion, and then understand how we can work out the maximum speed and the maximum acceleration in an oscillator's journey. So if you've been successful and you've learned in today's lesson, you can describe the characteristics of simple harmonic motion, explain the condition needed for simple harmonic motion, and use the equations for simple harmonic motion. In upcoming lessons, we'll look at how we can express this graphically. Thank you very much, and I hope you have a lovely day.